Well, hello and welcome to a fluids video. This is Ron. I'll be your teacher today. And today we are going to look at impulse and momentum for fluids. Now, just a quick refresher of what impulse momentum is. It's really has to do with force and time on one side and mass and velocity on the other. And I'm going to do mass times change in velocity because it's only if you change the momentum that you get an impulse. So as we transition this to fluids, what I'd like to do is I'd like to take the time and get it out of the left-hand side and bring it over to the right-hand side, and lo and behold, we get that force is equal to mass flow rate times change in velocity. Now, force is a vector, so the way we end up doing this is force in the x equals mass flow rate times a final velocity in the x minus initial velocity in the x, and then force in the y equals mass flow rate times final velocity in the y minus initial velocity in the y. And it doesn't matter, I always interchange those accidentally, whether you go x final or final y, doesn't matter. Okay, well that should make some sense. To show you an example of how this works, what if I took we call it a vane. What if I took a vane and I had some fluid flowing into that vane? So here's the fluid. And that fluid, when it's in the vane, ends up changing direction 180 degrees. Now, if you want to change direction of something, you have to apply a force. And of course, with Newton's third law, we could say that the force that the vane applies to the fluid, and that would be a force in the x direction to the left, because the vane is turning the fluid around. And with Newton's third law, that would be exactly the same as the force that the fluid applies to the vane. An example of this is in a steam turbine. The blade of the steam turbine often looks like this. It's called an impulse blade. Huh, wonder why. Impulse blade, that's funny. And it applies a force. So it's either the fluid applying a force on the vane or the vane applying a force on the fluid. So this force in the x would depend on, well, it would depend on how much mass is flowing in that stream of fluid. Is it 1 kilogram per second? Is it 1,000 pounds an hour? So the more the mass flow rate, the more force it would take. And then the final velocity in the x minus the initial velocity in the x. Well, let's anytime you do some of the forces in the x and so on, you have to choose a direction to be positive. So let's choose to the right to be positive. So that makes this is minus. Final velocity in the x is minus. Initial velocity in the x was positive, but we have a subtraction going on there. So you can see that this ends up doubling in the case where I turn the water completely around. These don't cancel each other out. They end up doubling. And the force in the x then would equal mass flow rate, doing the algebra here, times final velocity in the x plus initial velocity in the x. And that would be double the velocity. And really, that's all there is to it. That is, in and of itself, the impulse and momentum principle for fluid mechanics. Now, what would happen if I took that vane and changed its geometry some? What if the vane only turned the water straight up? So here comes the water. And it turns it straight up. I want you to use a little intuition here. what do you think is going to happen to the force in the X? Is it going to be more than when I turned the water completely around? Is it going to be less? Or will it be the same? My intuition tells me it's going to be less. That to turn that water all the way around would take more force. Well, let's try it. Force in the X equals mass flow rate times final velocity in the X minus initial velocity in the X. And what is the final velocity in the X? It's 0. It's not going in the X. It's going in the Y. So whereas before the force in the X was the sum of the two velocities, here, and again we can change the signs, the force in the X is going to be mass flow rate just times that initial velocity. And hopefully that worked with your tuition. I've seen vanes that look like this, where the initial velocity in the X coming in was to the right, and the final velocity in the X is to the right. This is going to require even less force than this, which turned it a full 90 degrees, and this, which turned it a full 180 degrees. Maybe this is only turning it 50 degrees, and so on. Now, some fun examples of this are like when you plow snow. It works the exact same way whether you've got a fixed vane and the fluid is coming into the vane at some velocity, or if you've got a fixed fluid, think of snow like a fluid, and you've got the vane coming at the fluid. So think of the vane as being your snow plow, or even a scoop shovel, or not a scoop shovel, but I just was out in the garage and I saw one of those shovels that looks like this. So when you plow, or when you shovel the snow comes in and turns around. It's the exact same thing. And the force that you would need to push that snow is dependent on these things. How fast are you moving? How thick is the snow? How dense is the snow? And how much do you change the angle of it? This is why people who have plows on their four-wheeler or on their truck will often take that plow and turn it a little bit so the snow coming in continues along some of that path. Now, why would you do that? Well, it's this reason right here, so that you can use less force to move that snow. When you have your snowplow arranged like this, it takes a whole lot of force. And of course, nobody wants to have their snow go straight up and land on their vehicle. But when you do it something like this, you can push the snow off to the side. It takes a lot less force. So there you have it, impulse and momentum. Hopefully you come up with some questions. As the course rolls on, we will do some example problems. We'll do some problems with this. And this is really the last scheduled video for the fluid mechanics course, if you're watching the video for fluid mechanics. If you're watching it for physics or something like that, then just ignore me and have a great day.